Well, this is it. This is the last video lecture for Natural Science 116. Natural Science 116, video lecture 10. And I'll start with some announcements. First of all, we should turn in any and all work by Friday of this week, so the 8th of May. And whatever you have you want to turn in, get it to me by then. And the second announcement is that the final exam is on the 14th. That's Thursday morning at 8:45 to 10:45. This will run just the way the midterm went, which went well, so I'm not worried about that. I'll send the exam out a few minutes early, but we really want to maintain this deadline. Okay, so by 10:45, taking your clear pictures, send them in to me. I'll give a little heads up on that. Maybe I'll send you another email, but basically we know what to do. And above all, make sure you always try to answer every problem, at least partly, so you don't get stuck on one and then miss answering some other ones. Yeah, so that's how it's going to be. And let's begin with, let's see, where's my pen? Let's begin with a review. So what I want to do here is just put together a list of everything we've touched on the entire semester. The point of the whole exercise was to integrate everything we needed in order to talk about energy, and that is why we started out the way we did and ended up the way we did. The logical order of it was such that everything that we touch on is going to need something that we did before. And so when we finally got to solar energy, for example, we needed to know about the theory of heat. We needed to know about electromagnetic rays, because that's light, heat transfer by radiation. And then because of the solar thermal power plants, we needed our heat engine discussion. And because of photovoltaics, we needed the electricity discussion. So in that sense, that's how the logic was, but we've actually covered quite a bit of stuff. So here we go. I'm just going to number these things as they occur to me. So we actually started with the hunt and some logical inference that takes place during the hunt, and that's where we came up with the sundial. Okay. But in order to talk about a sundial with any kind of accuracy, we needed geometry. So for that reason, we covered some of the geometry. And it turned out, for example, to talk about the number of days in a year, we also needed arithmetic. So we studied those things. So we had geometry and arithmetic. Yeah. Then we did this number of days in the year business, talking about sundials and things again. So the year, which necessitated some discussion of astronomy, but of course without geometry, astronomy is nowhere. So we had the geometry to talk about astronomy, and we got the shape and size of Earth, right? And it turned out that needed geometry and astronomy as well. So we figured out the size of Earth was an important topic. If you're talking about the energy needs of civilization which inhabits the entire Earth. Good, so that was that topic. You know, this is what the table of contents of your book would contain as well, so I should have given a heads up on that, but the review is good for that as well. Yeah, so what came after that? Then we started to talk about forces. In order to talk about forces, you have to have the concept of the vector. In order to have the concept of the vector, of course, you have to have geometry again. So we had the discussion of forces. And remember, we were also able to talk about structures, bridges, aqueducts, arches, and so forth. So that came into that discussion as well. So I'll write structures here. And then later on, we talked about dams, right? The dam was an interesting geometrical structure sometimes. Hoover Dam, for instance. Good. So what followed that was the discussion of work. In fact, I'll put them in order then. So you've got your concept of force, work, and then suddenly you know what energy is. Okay. And we also had power as work over time. So let's keep this list going here. Force, work, energy, and power. Then what? Power actually involved energy per time, and we touched on motion at that point, and we found we had to talk about motion a little more. At some point we talked about the grandfather clock and the pendulum, right? We've actually talked about the grandfather clock on both of our exams. So that was an example of that. I'm not going to put all those things down, I'm just giving the outline. So then we had to talk about motion and we were able to talk about free fall, and we were able to talk about accelerated motion, velocity, orbital speeds, so orbits of satellites. And we needed this topic in order to improve our understanding of energy, because then we had to talk about kinetic energy first. So then we went back to energy work, kinetic energy, conservation of energy. Okay, I got to make sure I fit all of this on these boards, because then I'm going to go and underline the stuff where I intend to put exam questions, or the stuff that I intend to use in our exam questions. But let's see if we can keep going with this list. So then we had conservation of energy, and at this point we were ready to talk about hydropower. So hydropower, I always said, that's central to the entire course. We'll definitely have something on hydropower again on the final exam. Remember, we had that power formula, and it used so much, okay? We had to know what G was. We got G from the discussion of motion, and on and on. So the hydropower, see if I have any other note here about the hydropower. Important. It was central because when we did that big hydropower cartoon, it also contained stuff from later on in the semester. Okay, so it took all of that to get to hydropower. When we were done with that, we started talking about thermal physics. Okay. So thermal physics, which we started very basically, sensations, hot and cold and so forth. So can't write all that, but let's say we went through heat, temperature scales, heat, mechanical equivalent of heat. That I want to write down. Mechanical equivalent of heat. Okay. Then we had, in thermal physics also, we had states of matter that we needed to know about. We needed to know about heat transfer. And from that, we were able to motivate the idea of entropy. Kind of a sophisticated concept, but we made good use of the entropy later. And remember, here the whole thing is this cartoon, right? TH to TC. So we did states of matter. And this allowed us to talk about the heat engine. Heat engine itself is a pretty central point in the whole lecture. We're talking about anything from our automobiles to power plants that drive the whole, power the whole civilization. So the heat engine was very important. We used the entropy discussion to get its efficiency. Then on my list, I have electricity. And because of the way we built things up, in particular with our hydropower formula, we were immediately or almost immediately able to get to the electrical power formula. So electricity and the household power. But those formulas that we use for household power, they can use those for the entire civilization as well. Watts, joules, amperes, volts, so forth. So, but this is something we'll have a question on for sure. Then I have magnetism, or let's say electricity and magnetism. Electricity, magnetism, plus laws of electricity and magnetism. And then 14, motors, generators. And I'm going to put in parentheses transformers. Actually, a very interesting topic as well, transformers, really would fit in. We didn't quite get there. If you want to look something up about transformers, if you look up information on transformers, you'll understand it, right? It'll fit right into the discussion we already had with these things. Okay, so motors, generators, transformers, and then the grid. Now the grid I didn't really talk about the way I wanted to. And I'll also put here pipelines, right? So gas, oil, pipelines. The grid ties everything together. So I mentioned it briefly, but it's a good topic in its own right if you're getting this whole overview of energy. So the electrical power grid, a topic we didn't have that much time for, but this is where it goes, fits in the progression. Then solar energy. We had already mentioned solar energy way back with the hydropower because of the water cycle. So we had solar energy and the solar constant. Very important here. How to measure that power per area, right? The intensity, how to measure it. We'd had solar energy back here. Here, after doing thermal physics, we learned how to actually measure the solar constant, okay? So that was important in that regard. The other thing in solar energy, getting towards the end of my list, is the applications. So I'm just gonna write solar here again. There's the photovoltaic, direct transformation of solar energy into electrical energy. So you've got the photovoltaic and you have the solar thermal. The kind with the central tower. That's about as far as we got, isn't it? I'm going to put something else on my list in parentheses because we didn't talk about it. Wind energy. It's convection, so we learned about it back in heat transfer mechanisms. And I have a section on wind energy that we didn't have time for, where we can actually quantify how many watts per square meter is present in an air current, and then you can figure out how much your giant turbines are going to be able to deliver. So that fits in, that's in the schema as well. And I didn't get to nuclear energy, but there's an interesting discovery, namely, in a sense, nuclear energy was discovered by analyzing the solar energy. So, yeah, short discussion. Knowing the solar constant and knowing the size and the distance of the sun to the earth and everything allows one to immediately calculate how powerful the sun is. And it turns out the sun is so powerful that it could never be produced, the solar energy could never be produced by chemistry, by chemical energy. So that allows one to infer the necessity of there being nuclear energy. Anyway, that's as far as I ever get in this class. We didn't get these two topics. They're in there if you ever want to, you know, they're available to you, and you would understand them if you just put them in this order now. So there you have it. That's our entire semester. And of course, you've downloaded endless pictures of these various things. So hopefully you have some sort of book together. I will also say that you won't find this progression of ideas covering the whole topic of energy. You won't find it anywhere else except in your own book that you've taken, the notes you've taken. Although it's all very standard material, you can look it up, but this progression here is something that we did. Okay, what about our exam? I'll just make it up on the spot. What do we want to have on our exam? Red or blue? Blue. Definitely we need force, work, energy, power. Okay. We need, as a question, or, you know, be ready to answer that kind of question. And in the progression also, kinetic energy, conservation of energy. Okay. That just as background material. You have to have your formula sheets ready and be able to talk about those things. Hydropower in some form or another will be back in the mix. And when it comes to thermal physics, definitely a heat engine type of problem. The reason being is that our central tower solar thermal requires understanding of a heat engine. Our solar chimney, by the way, which I don't have on this list here. Well, yeah, the solar chimney was under heat engines, and that requires that whole discussion as well, and it's wind at the same time. Okay, so interesting thing. Electricity and household power, so those watts and volts and energy conversions, those kind of things, watts, volts, kilowatt hours, that kind of thing. We did a couple problems on. Definitely a question on that. The laws, that's kind of difficult. We won't worry about that, but this was an important applications thing, so I could put a couple things of that type there. The solar constant, how the solar constant is measured and what it is, those 1340 watts per square meter. And then I saw someone else claims it's 1360. Okay, well, 1340, 1360, it's all good. So solar energy, solar constant, how it's measured is a good topic. And then this part here with the solar thermal, which ties everything together. So that's roughly what I wanted on the exam, but I had an idea. It's not on our list here. Let's see where we would fit it in. You know, here's not a bonus, but an important example. The Arizona Meteor. I'm thinking I'll try to put some kind of question discussion about the Arizona Meteor in there. The reason being is that thing's coming from outer space, and So it involves astronomy in a sense. It involves satellite orbits also, in a sense, because the speed of a meteor can be estimated roughly as the speed of an orbiting satellite, or at least greater than the speed of an orbiting satellite. But that's the magnitude of a speed like that. Also, when the meteor has mass, it has kinetic energy. Okay. When it's far away, it has potential energy. The potential energy, did I put potential energy up here anywhere? Yeah, potential energy, of course. Potential energy, okay, very important, potential energy. Yeah, it has potential energy converted to kinetic energy. When it hits the Earth, that energy is converted to heat extremely rapidly because it comes to a stop. If it's moving 10,000 meters per second, it comes to a stop in a split second, fraction of a second. Okay. And you can even calculate how long it takes for it to come to a stop. You know, it's going to be 1/10 of a second or less. And all that energy, boom, turns into an explosion. So the Arizona meteor is a good example to discuss a lot of our concepts, going all the way back to astronomy, motion, energy, conversion of energy, transformation, power. It's all in there. So yeah, I'm going to think about that a bit more, but it fits in really nicely. What did I say in the lecture? The work of excavation. So the meteor leaves a crater behind, and so all that dirt was lifted out. That itself is work. Dirt and rock and what have you. Okay, good. So there is, for starters, our outline. I have one more idea for an assignment. Let's see, I think we have plenty of time. I don't intend to make this lecture all that long. Well, time flies, 20 minutes. Yeah, I had this ambition of the all-time cartoon, and I'm just gonna sketch it out. You guys can flesh it out. Maybe you can make the all-time one-page cartoon. What I'm thinking of is the hydropower cartoon, except we could try to build in everything. That would be a good goal. I've never done that before. So anyway, here's your list before I erase it. Once again, just kind of looking over it. And once again, the order goes. So the logic of all of this, you know, we started at the primordial point of just hunting. We used the sundial to communicate information about the time. We needed geometry to do that better. We needed arithmetic to do that better. To have a civilization, you have to have a calendar. We had to know about the year, but the year is an astronomical quantity, actually, size of Earth through geometry. All these things are necessary. In a sense, they're kind of historical. This is why we start with ancient history here. And they all tie together nicely. Structures, forces, and so forth. Okay, so that was just to bring it back to you guys, that was, now that you see it in retrospect, that was the whole idea of what we did all semester. And especially if you can include transformers and electrical transmission, power transmission, which we didn't do, but we could have, we just ran out of time, and the grid, and then wind energy and nuclear energy, then you really have a complete overview of what's necessary. And I'll remind you, we've done these things quantitatively. So let me put that up here as well. We've done everything quantitatively so we can actually convert. So I'm going to write here energy conversions. So we can convert the kilowatt hours on our bill, on our electricity bill, for instance, we can convert that to a certain amount of water in a lake above a power plant. Okay, we could convert it to a certain amount of heat of combustion in a chunk of coal, or another piece of fuel. So yeah, we've worked quantitatively, and if you have the time and a piece of paper, you can just pencil in all the needs of energy needs of civilization. So that was an important goal in the course too. Now, whether you feel confident to do that, you should feel confident that you've seen it done and that you know it's there to be had. It's there to be understood. So yeah, when I'm talking about energy conversions, I'm saying we have kilowatt hours, we have joules. We know the joules are M times G times H, which is the lifted weight. So all of those things that we've studied as well. Okay. So let's end with what that great cartoon would look like. I really want to leave that up to you guys. So up there where I said turn in any and all work by Friday, if you come up with a good cartoon, take a picture of that too. Let's see what it would all incorporate. You know, I don't think we would incorporate the Arizona Meteor in that cartoon, although if you get creative, maybe you can do that too. You know, maybe the meteor came in and blasted a hole in the ground and we use that for the lake, okay, but then again, maybe not. So yeah, the energy cartoon. You know, we originally had our dam, okay? Now, it would be interesting to talk about the structure of those dams in terms of that curved shell structure, which is holding the water back. Then we would have actually been talking about vectors as well. But, you know, we would have our dam and our penstock and our power plant here and our lower lake, and we'd still have the height H. Okay, we'd still have the mountains behind there. But now what else do we have? We have solar thermal power plants. We have ordinary power plants. We have nuclear energy power plants. So we have heat engines in there. We can take the power from them back into the, in terms of pump storage. It's all tied together by the grid. So yeah, the total energy cartoon, you'd need the full board here, and you could have a solar chimney, solar thermal power plant, central tower, the works. That's my idea for that. So something like that would make a good, would make a good cover, opening cover for your book as well. If you come up with something nice, send me a picture. I'd be interested in seeing it. Okay, it would definitely be. So I'm just going to write here plus, just to indicate what could be on the list. So pump storage, and the grid is in here because that's what ties everything together. All these different energy sources are tied together by the grid. You've got solar, thermal, I'll just write central tower style. You have photovoltaic on your rooftops. In the city, in the residential, I mean, it's a good place to put them. Everybody's got a roof. You've got wind turbines. You've got ordinary coal, oil, gas, nuclear, all of those types of power plants, they use heat engines. Okay? These are just different ways of generating the heat to get the energy. So yeah, there's my idea. You even have the what was that? The solar chimney, etc. Wind plus solar chimney. Okay, there's a world of stuff. I'm not sure how you build in the satellite orbits into this thing here, but you know, maybe you can. Good. So I'm just going to try to remind myself if I've missed anything. So once again, turn in any work you want to turn in by Friday of this week. That's the first thing. The exam is next Thursday, so we're going to maintain the schedule here, 8:45 to 10:45 a.m. and have it all back to me by 10:45 with clear pictures. And otherwise, good luck to everybody on this exam and on all of your exams. Okay, we'll see you next time.